welcome you all to today's lecture. So today we will continue with the next part that we will discuss today about static error, constants and system types. So just an overview what we did till now. We are looking for steady state error, and steady state error is the one when we have transient response is over and after steady state time is reached by the output, we will look at the difference between the input and output. We call it as steady state error. Now, then we discuss uh, what steady state error look like for a unity negative feedback system, and for different inputs. For example, we look at for step input, then we discuss for ramp and parabolic. Okay. Now, because steady state error is also a very important specification, so as we define the ramp damping ratio on natural frequency, settling time, percentage overshoot, and so on. So performance specification is for transient, also for steady state is for when we discuss the performance parameter for steady state, we discuss the static error constants. Okay. Now let's see what do you mean by static error constant. So the specification of transient response is overshoot, damping ratio, natural frequency, settling time, rise time, and so on. For steady state, we have static error constants. So in today's lecture, we will look at what is static error constant and how we manipulate it for system type. Now, first of all, static error constant. So we will move to the previous article where we discussed the steady state error with step input, parabolic, and ramp input. So I just plug in the formulas with open loop transfer function. For the first one is the step input. After applying the final value theorem, I come up with 1 over 1 plus limit s tend to 0 g of s. Similarly, for ramp input, it is e infinity ramp 1 over limit s into g of s. Now the last one is for parabolic. So as we know that parabolic is 1 by 2 times t square u of t. So in that case, it becomes 1 over limit s square g of s. Okay. So these are three relations that we developed in previous section. Now, in previous video we discussed these. Now the next thing is, if we look here for step input, the main idea here is the limit when s tend to 0. For ramp is limit when s tend to 0 s times g of s. So we call it the for equation 7.3 for a step input, we call it as a position constant. So when we represent this kp by limit when s tend to 0 g of 0, we call it a position constant, because we will get this relation for a step input, and for step we already discussed when we start the steady state error that step input is for position, ramp is for velocity, and parabola is for acceleration. So that's why we call it as position constant, and limit when s tend to 0 g of s is also known as position constant, and it is represented by k subscript p. Okay. So similarly, the next constant we represented by velocity constant, because this is due to the parabola, and velocity constant is limit s tend to 0 s g of s. So velocity is with the ramp, so we have to go for ramp. Sorry, not parabola, ramp. Parabola is for acceleration, ramp is for velocity. So that's why we represent this by velocity represented as kv is equal to limit s tend to 0 s g. So Similarly, the third one is because when we discuss the ramp input and we say that this is actually a acceleration. So for parabola is an acceleration. So in that case, we discussed acceleration constant. As for ramp, we have velocity. As for unit, we have position constant. Similarly, we have for ramp, we have acceleration constant represented by kf. Kf is limit when s tend to 0, s square g of s. Okay. So these three are actually the specifications that we can use, and these are actually specifications that tell us about the steady state error of the system, and this is also known as static error constants. So first one is the position constant, second is the velocity constant, and last one is the acceleration constant. So only difference here is position constant is without s times g of s limit, kv constant as single s, and acceleration constant as s square. Now g of s is actually open loop transformation. To remember this thing, okay? And this is only true for unity feedback system. Now let's look at example how we manipulate and use this. So for that example, we have three systems given to us with different GFS here. Look here, for this GFS, there's no pole at the origin. There's one pole at the origin. There are two poles at the origin. Let's see how we manipulate or calculate the position. So for this position constant, we have to take the limit when s tend to 0. We put 0 here, 0 here, 0 here, 0 here. So it becomes 500 times 10 divided by 8 times 10 times 12. When we solve it, we easily calculate the position constant. Look here, position constant becomes 5.208. Similarly, when we calculate the velocity constant, that is kv, if you remember, it is limit when s tend to 0, s times g of s. So when we plug in the values, we know that when we put the limit g of s, we already know from kp it becomes 5.2. When we multiply by with s and s value 0, it becomes 0. So kv is 0. Similar, what about k? K is also 0 because s square is multiplied. Because g of s has constant values, so that's why. Now if we move to next one, for next one we have to put s0. When we put s0 for kp, this becomes a number divided by 0. It becomes infinity for kp, but finite for kv and 0 for ka. Okay, look here, just plug in the formula. So thus for step input, steady state error is 1 over kp, and we just put in kp is equal to this. For ramp is infinite, and for parabola is also infinite for first case. Similarly for second case, kp is infinity. I just because due to one pole at the origin, kv is a constant, so k is 0. Just calculate the step input error. 1 over 1 plus kp is 0 because kp is infinity. Steady state error is 0. As we know that there is single integral, so that's why step steady state error is 0. For ramp is actually a constant, steady state error for parabola is infinite. Similarly for third one, because we have two poles at the origin for open loop system, so this means that kp has what you say infinite. Similarly kv is also infinite, but k is finite. So when we look at the steady state error, for unit step is 0, for ramp is also 0, but for parabola is a constant. So just plug in the values. You look here, kp is 0, 0, and you do calculation by yourself. You will get the idea how I calculate these error constants and the steady state error for different inputs. Now the last thing that we need to know is known as system types. So if you look at the response, especially in this example, so if I go back and look at the transfer functions that are given to us in this example, so look here, the only difference between all three block diagram is the this there is no S here, or in other words, there is no pole at the origin. There's one pole at the origin. There's two pole at the origin. So the number of poles at the origin is also equal to the system type. So if there's no pole at the origin, we say that system type is 0. If there is single pole at the origin, we say that system type is 1. If there is two poles at the origin, we say that system type is 2. So because these number of poles will affect the error of the steady state error of the system. So from here we defined system type. So this means that steady state error depends upon two things. First is the type of the input, and second is the type of the system. So that's why we need to define, for input we already defined the error constant. So for system we have to define system types. Okay, so that's why we define system type here. Let us continue focus on unity. Again, negative feedback system. The value of static error constant again depend upon the form of GFS, especially the number of pure integrals in the forward path. Since steady state error dependent upon the number of integrals in the forward path, we give a name to this system attributes. So number of integrals in the forward path are in open loop system. We call the number as a system type. Okay, so this means that if there's no integral in forward path for open loop system, the system type is 0. If there's one, system type is 1. So look at this block diagram here, where we have input and output. We have open loop GFS given to us. So for this GFS we have to define the type. So we define the type using open loop transfer function GFS. So that type tell us about the number of poles at the origin. So this S power n, if n is equal to 0 means that there's no S available or no integral, so system type is 0. When n is 1, system type is 1, and so on. So this is the basic information that tell us the system type. Now we are ready to comprehend or represent the whole information about the steady state error in terms of a table that tell us the relationship between input, system type, static error constant, and steady state error. So because I told you that steady state error depends upon the type of the system and also on the input. Now let's consider an input here. So we have three inputs we are considering for our analysis purpose. First one is the step input, second one is the ramp input, and third one is the parabolic input. So you have to remember that step input you just represent u of t, ramp is t times u of t, parabolic is half t square u of t. Okay. Now when you look at the steady state error formula, so that we develop for step input is 1 over 1 plus kp, for parabola 1 over kv, and for parabola 1 over ka, for ramp is 1 over kv. Okay, so these are the formulas that we developed for steady state error based on error constant. Now here error constant kp is a constant when we have a type 0 system. Okay, because for type 0 system when we give a step input, then in that case we have a constant error. But when we give ramp input, because of the if you look at the ramp input we have t times u of t. So when you look at it becomes 1 over s square. So if we take 1s make a part of the system and other 1 over s make as a step input, we know that if there's an integral in the system and with step input, in that case error is 0. So look here, same thing happened for ramp input because it becomes 1 over s square. That makes the for system type error is 0. The kV is 0. Similarly for parabola, again we have 2 cube s cube is coming into play, so that's why Ka is also 0. Now we know that this is the steady state error formulas. When we plug in Kp as a constant, so in that case we have this error for type 0. Kv is 0, so it becomes infinity, so error becomes infinity. Okay, so remember that if you have a constant error for step input, for higher inputs your error must be infinite. If you have a constant error for ramp, in that case higher parabolic one is infinity. Okay, now look at the type 1. Type 1 means that you have a single integral, so in that case Kp becomes infinity, Kv becomes constant, and Ka is 0. Okay, so because of infinity error is 0. Now because type 1 system has step input with 0 error, this means that the ramp input has 1 over kV, a constant error, but parabola is infinite. So similarly, type 2 system where we have two integrals coming into play, and in that case we have error constant, kp is infinity, kv is also infinity, k is constant, so it becomes 0 0 1 over ka. So look here, if you look at the square t square, so this means that this represents type 2 and with a constant error for parabola. T power 1 is type 1 with a constant error. Okay. T power 0 type 0 with a constant error. So remember that. So in other words, you can apply the formula to develop this table. This table helps you to look at how error behaves with different inputs and type of the system. Now this is the example. You just pause the video and try to solve this skill problem. Now I will stop here. In next we will discuss how we can use steady state error specifications as a part of design. Thank you.